Welcome to another episode of Code for Thought. Finding new and sustainable energy sources is more important than ever. Nuclear fusion, that is, harnessing energy in the way our sun does, has been an ambition for a long time. Over the past year or so, we've seen a number of announcements saying that we are getting closer to the point where it can actually be used for energy production. And with that in mind, it gives me great pleasure to talk to Adam Stephen from the UK Atomic Energy Authority. Adam is based in Culham, and as Director for Innovation, he supervises important parts of nuclear fusion technologies, in particular real-time systems and software. And here now my conversation with Adam. Hello, Adam. Thank you very much for coming to the show. I think we have a very exciting subject today, real time in nuclear fusion. So two very exciting subjects. But before we go into that, maybe you can introduce yourself quickly.
Sure, thanks, Peter. So I'm Adam Stephen. I got into science at an early age. My first scientific job was cutting blades of grass to do agricultural research. And I moved on from there to do a degree in physics and maths at St Andrews University. I was sponsored there by the National Physical Laboratory. So in the summers, I went down to London, and there I moved on from blades of grass to going to collect cows' livers on a Monday morning and doing some studies of the effect of ultrasound on heating tissue. That was one summer. And then I had a summer filming helicopters to work out how much noise aircraft make and how much compensation the government owed various people as a result. So all interesting physics and experimental tasks. And that got me through most of my undergraduate. At the end, I was getting into lots of theoretical physics, particle physics, and I went down to CERN for a summer. That was partly because not only did I study physics, I was studying French as well. And that turned out to be a really good move to get through the application process at CERN. So a summer down in Geneva, studying particles. But at the end of that, I decided I was more interested in working on something ethical, and climate change was a big hot topic even back there in '94. And so I chose to do a PhD in atmospheric physics. That was 4 fascinating years at Oxford, studying fluid dynamics, experimental work, programming a lot of stuff as well to do the data analysis, to do the experiment control. And so at the end of that, I decided to move into computing as a career path. I had 2 job offers. One was to work for a Formula One telemetry company, and the other was to go and work on the JET, Joint European Torus, on nuclear fusion. And as a theoretical physicist, I'm afraid Formula One lost.
Yeah, it wasn't exactly a tough sell, was it? Yeah. So what actually interests you about nuclear fusion then?
It's a great space to work on. I mean, the reason we all do it fundamentally is it's a source of carbon-free clean energy. And at the moment, that's important not just for net zero, which is a big driver of the funding, but also for security of energy supply. So the motivation for everyone is obvious. The typical question, therefore, is if it's so great, because fundamentally, take some seawater, heat it to 100 million degrees, and you're going to get loads of carbon-free energy. The usual question is, so why aren't we doing that? And the answer is slightly that it's tricky, and partly that it needs a lot of investment, but we're at a tipping point where that's coming now. If you ignore the social benefits, what are we doing? We're taking protons and we're smashing them together inside an ultra-high vacuum. We're trying to keep it there with really strong magnetic fields. The plasma demonstrates all kinds of fascinating instabilities and esoteric physical behaviors. To do all that, you've got to control processes. Some of the measurements are at gigahertz. The control loops can be at 20 kilohertz. Somehow you've got to make electronics and computers and software manage all that. And that's just a fascinating set of technology challenges to work on.
The way we can imagine this, there's a test reactor, isn't there, sort of at the site where you're at?
Oh, we have 2, actually.
Or you have 2, in fact.
Yeah.
Exactly. And more are coming. I think one is being built in France at the moment.
Oh, yeah. I mean, and across the world, there are hundreds of these devices and lots of variations. But yeah. So we have a test reactor. If you're technical, and particularly if you speak Russian, it's a tokamak, which stands for Toroidalnaya Magnetskaya Kamera, so a toroidal magnetic chamber. If you're non-technical, it's a donut, right? It's a big steel donut, and we pump out all the gas from it, and that's the basic starting point. You can think of the core of the donut being where the the protons tend to collect. And we organize the magnetic fields to squash them down into a tight ring in the center because we want to achieve high pressures and high temperatures. So the protons are going round and round the donut. The electrons are moving at about 10% the speed of light. I don't know the ion speed, but if you convert 100 million degrees into ion speed, it's a very, very, very high speed. What can go wrong in terms of instabilities is that bunches of protons can start to deviate from this compressed, stable path that we're enforcing with our magnets. Under certain conditions, those instabilities grow. If you were to sort of look down on the top of this, you'd see that rather than having a circle, you see a bulge starting to form, and the bulge would kind of form and rotate. You might get a second lobe, and eventually the excursion from the center becomes large enough that the stream of particles hits the wall of the vessel. Now, at that point, that's the end of the generating fusion, and that has two consequences. Firstly, all this high-energy set of particles slam into the wall, and they can do some material damage to the wall. But secondly, the mechanical forces that we're exerting on these protons, and there's 1/10 of a gram of gas, something like that, so it's a very, very tenuous atmosphere. 1/10 of a gram of gas, and we're pushing on that with a force of several hundred tons. And that's okay, because the plasma's pushing back with a force of several hundred tons until the instability slams it into the wall in a millisecond. And then our magnet forces are transferred onto the vessel. And so we've got to very rapidly reduce the currents in the magnets. Now, along the way, we're heating it up by injecting energy in all kinds of interesting ways. Usually, when the plasma's behaving normally, nice and dense in the middle, all the injected energy gets absorbed, and that's what we want. But if we have one of these excursions, which we call disruptions, by the way, then suddenly there's nothing there, because it's a near ultra-pure vacuum. So if we continue injecting our energy after the plasma has vanished, then that energy will go through and strike our vessel walls and potentially damage them. So it's the job of the control systems to be measuring the density, for example, with laser interferometry. And if the density is high, keep firing the energy in. But as soon as it goes away, you've got to ramp down that energy injection. So we've got to keep the stability for the process to work, and we've got to avoid breaking our machine when abnormal plasma conditions are experienced.
So how likely is it that these instabilities actually occur?
Oh,
and what can you do to actually counter them?
Yeah, so we've got a bunch of levers. Firstly, we can vary the magnetic field, and that gives us direct handle on the particles in the plasma. We can vary the heating. So we've got heating using radio frequency waves, using microwaves. We've also got a neutral beam injection system, which is it's usually described as like frothing the milk for a cappuccino. So in that case, you put hot steam into milk. In our case, we put hot helium and hot hydrogen into the plasma. So we can vary the quantities of that heating and the places in the plasma where it gets absorbed. We can also inject more gas, so that will tend to sort of cool things down a little bit. We can actually fire little tiny snowballs of frozen deuterium right into the core of the plasma with what we call a pellet injector system. So all these different actuators used in different combinations, and the research is finding out how to do that control. Those are the ways we can change the behavior of the plasma.
Are these instabilities what's stopping us from using that as a commercial system these days?
Not really. If you'd asked me that question when I started my career 25 years ago, the answer would have been absolutely yes. To start with, they were an unexpected phenomenon. So addressing the engineering to make the machine more robust was important. Then studying how they occur was important, classifying them. There's also kind of esoteric physics terms for neoclassical tearing modes or snakes or other such things, because that's what physicists like to do. Basically, what would happen 25 years ago is we'd collect all the measurement data, we'd crunch the numbers on an IBM mainframe, and then we might be able to say, we now realize that an instability had set in, and had we but been able to predict it, we could have done something about it. Moore's law has come to the rescue. So over 20 years, algorithms that would have run in the mainframe after the experiment now run in real time. And so they give us predictions of the instability ahead of time so we can take action to avoid it. And we do a lot of studies to see whether our techniques for doing that work. Some of the state of the art in this is using machine learning, AI for pattern recognition. I think the challenge for the future machines is we generate these stabilities on our current devices to study them. So we intentionally provoke them, and then we see whether we can recover. The future power station class machines, we're not going to do that. We will absolutely engineer it to avoid these, Because firstly, they're going to stop the production of power, which is bad news for the economics of the machine. And secondly, they are a little bit of a risk. But largely, that problem, that plasma physics problem, that control problem is pretty well understood. And we're moving these days more onto larger engineering problems. For example, while the plasma's going stably, huge amounts of radiation are coming out to our exhaust structure. It's having to absorb heat loads of sort of 20 megawatts per square meter. Now, we've got materials research making good, robust structures that can withstand that. But even more than that, the second machine on our site, which is a UK experiment called MAST, it's been upgraded over the last 5 years or so with a brand new exhaust system with additional magnets. And those additional magnets are used to smooth out the power loading on the exhaust so that it will last for a longer time and be more economically viable. So we're going from sort of fundamental plasma questions, which were the challenge 30, 20 years ago, to more engineering pragmatic questions not to make fusion possible, but to make it economically viable and attractive.
So let's talk a little bit about your contribution there, because you're working on real-time systems. What kind of real-time systems are they, and what is your role in this?
I should emphasize this is very much a team effort with colleagues across the globe. The challenge for my team, who are at that interface between measurements have been made, the plasma is waiting for us to do something with the levers to keep it stable, and we've got a budget of maybe a millisecond, 2 milliseconds to do all the calculations, to make the decision about what we do, and then to ensure that those injections of gas and energy, heating and fueling, achieve the physics aim.
Well, one of the questions that I have, because when we talk about real time, there's always a little bit of a time delay. So your time window, really, when we talk about real time,
So the timescales, it's like most physical processes. There are characteristic timescales. They depend a little bit how big your tokamak is. So the timescale for the jet machine, which is pretty large, is quite slow. For me, 2 milliseconds is quite a slow timescale. The MAST machine studying the exhaust problem, that's got it's a more compact device, and so the dynamics are rather quicker. ITER, which is the machine in the south of France, is even bigger than JET, so it's even slower. And interestingly, we'll come back to the difference between slow, fast, real-time, and determinism in a second, but although I say ITER's slower, and your listeners might be thinking, well, that's good, it's going to be easier to control. It's not. If you imagine, if I gave you a bicycle to ride, and I said, there's going to be 3 seconds delay between when you turn the handlebars and when the wheel shifts, you'd probably find that much harder than if I gave you an instantly responsive system. We have timescales for various different physical processes. For each of those, we've then got to engineer either a measurement or a control system that can work within the constraints of that time bound. But when I say real time, what I mean particularly is must work without fail, with a maximum upper bound on execution times in all possible circumstances. For example, if you give me a physics algorithm that might or might not converge, depending on the values, and might take a different amount of time on different occasions to come to that decision, that's not going to be very suitable for the kind of controllers that we design. Everything from the electronics, the acquisition, the data processing, the filtering, the physics algorithm, the decisions, if there are decisions, the branches to alternative protection paths, if that's necessary, and finally, the actuator response, that always has to happen within the control loop time bound, which, as I say, for quite a lot of the processes I work on personally is around 2 milliseconds. We have a vertical stabilization problem that's a bit faster. That has to go at 20 kilohertz, so 50 microseconds is the time bound there. But in all cases, if we miss the cycle time for more than 2 or 3 cycles in a row, effectively that's the end of the experiment, and that's when the power will cut off. And that's a little bit like the problem of managing the national grid. I mean, if national grid doesn't balance load and demand for 150 milliseconds, then we'll have a big blackout problem. It's being always on time, never failing. And actually, the resilience and reliability is at least as challenging as the physics and the control problems.
Working without fail and being on time, they're individually quite difficult to achieve.
Yeah.
Because systems do fail every now and then. So how do you build such a system then? What kind of computing are we talking about? I don't think that you can walk into Curry's and buy a PC laptop. I don't think that's probably going to do the job.
Well,
Then,
you'd
is
be
it?
surprised. So, I mean, the tech we've used over the years has varied. We've gone through several different generations of embedded system. And indeed, one of the challenges is keeping a working design up to date as the tech refresh cycle goes through. But, for example, the class of machines I started off with in my earlier career, they were Power PCs running on embedded single board computers in an industrial rack using a specialist real-time operating system. I probably shouldn't name the vendor, but because there are many different real-time operating systems. And with that layer, the sort of programming and software engineering challenges were partly what I'd characterize as embedded systems techniques. So you want to be running deterministically. So you don't want to do any memory allocation, for example, during the control process, because maybe the memory is fragmented and suddenly it takes longer to allocate a buffer. So you do all your allocation up front. Anything you can do up front before you're into the critical period controlling a device with gas at 100 million degrees, you do up front. The other principle is you try to make sure that on every cycle, you do exactly the same sequence of operations. And designing for sort of stationarity is an important technique. And that can be counterintuitive. So, for example, if you've got inputs coming from different network providers, other external systems, because it's very much a distributed system, if there was an experiment in which one measurement wasn't required, you might say, oh, we can optimize the network and not send the measurements that aren't needed. But as a control engineer, I would much rather you send me zeros so that I still have the same behavior of the network stack. Don't care about the fact I'm not using the values. I want the same pattern of behavior every time to give me more predictability and repeatability. So that's one of the sort of things that we do.
Talk us a little bit through the technology stack there. Is it kind of off the shelf? Well, when I say off the shelf, the kind of open source, publicly available languages that you use, or is that something very bespoke for that purpose?
Yeah, that's a great question. There's a couple of answers to that. The things we were using 20 years ago, it was difficult. Well, firstly, 20, even 30 years ago when JET got started, the internet wasn't there. So everything had to be done on site. It tended to be quite bespoke. Even once we had the internet, early on, there weren't many advances in advanced Linux, in open source specialist techniques. So we bought proprietary real-time operating systems, and then we coded our own bespoke applications according to our internal needs. That's changed a lot. Sort of through the 2000s and beyond, we really got into open source. We're using real-time Linux on, in some cases, just commodity PCs, but using special techniques to isolate the cores, to separate where the interrupts go and how they get handled. And we've developed, a whole bunch of us across the Fusion community have developed a set of C++ libraries as a framework for real-time measurement and control developments. And that was the brainchild of an Italian electrical engineer, Filippo Sartori, who was a genius and had a great vision. And he built out this framework over successive applications. And it went from being in use here in Culham to being used in Portugal at the IST facility and in other labs in Europe. And it's gone on from there to be used across the world. And it's a very successful collaborative open source project.
So open source meaning that other people could also access it and potentially use it.
Yes.
Or contribute to it. If they
yes.
wish.
We had to go through, it's probably worth mentioning, it's not just the technical part of a project that's important when you want to go open source. Fusion is generally publicly funded, although that's changing. Billions going in private Fusion at the moment. But with public funding, you still have to get permission to share things that were developed by a certain grant or a certain research funding. And Filippo had the tenacity to go up to Brussels and get the lawyers and the sign-off to say we could release, the software is called Marte, which is a multi-threaded application for real-time execution. And he got the permission to release that under the EU public license, and that is out on GitHub today. And we've got about 60 to 100 active users in various institutions now.
Right. I mean, hats off to him to actually get this done and take the initiative. You mentioned normal commodity PCs that you use, but I think you're also using high performance computing. And I would like to understand a little bit more about under what circumstances you use that.
There's sort of two directions where we do highly specialist things. One is in the area of advanced instrumentation and measurement. And that's where we've got really challenging data rates, multi-giga sample per second ADCs, multiple channels measuring in space and time. For that, we're using quite a lot of FPGA technology, and increasingly the hybrid platforms where you've got both programmable logic and CPUs inside a single silicon package, and even with AI accelerators as well. That's using the latest, fastest compute technology for individual systems. And then the other really big trend, which is going to explode hugely in the next couple of years, there's a design methodology called digital twin. And the concept is, clearly we do physics modeling of the plasma, but when we're building a power station, a fusion power station, we've got lots of other modeling and simulation challenges too. So we've got to do everything from the civil engineering design, the electrical engineering design, all of the complex vessel, electrical, electronics, control systems, measurement systems, and plasma physics. So we're working on 7 or 8 different engineering disciplines. The traditional path would be one group make a decision. The vessel's going to be this big. And then you'd spend a few months or maybe even a year where everybody else says, okay, if the vessel were that big, what would the impact on our engineering discipline be? And they do some studies and you come back and agree, does that work or not? And that's a very slow process. Maybe you'd even do some prototyping. So with digital twin, the idea is, no, what if you could do all of that engineering modeling in one really large throughput compute environment? We've got an advanced computing group who are working at the real cutting edge of exascale computing. So these are supercomputer machines which are the top of the range on the planet. It's actually a research field within exascale computing to work out what techniques will make it possible to actually use those machines effectively for doing various workloads. So we're reaching out to them because we've got a scale of problem that needs that compute power. So we want to do full reactor design where all the different discipline modeling and simulation, from the civil through to the plasma physics and back, is tested in models and linked simulations, and we can explore the full parameter space. So rather than trying to design one workable machine, we can be looking to optimize the best of the machines across the full design space. And that takes a really significant amount of compute power and a whole lot of great techniques and technologies. And it includes, for example, the sort of civil engineering finite element modeling environment. That's not really geared up for scaling to cloud computing. It tends to assume, one engineer, one workstation model. So in some cases, we're even having to try and get engineering disciplines to retool to be capable of working on this much bigger horizon.
So there's a lot of exciting stuff then happening. Once it's there, it will speed up the whole process by how much do you think? It will certainly make it faster, which is the reason why you're doing it. But how much do you think you're going to get out of this?
Well, I was discussing this with my colleague who leads the advanced computing group the other day, and his strong belief on this is it's not that it just speeds it up, it's that it's an enabling technology without which it's not going to be possible to do the design work. As I say, fusion's kind of got beyond the can we make the physics work stage. We're on the how do we do the engineering and scaling up phase. And for that, it's questions of not just how do you make one, but how do you make hundreds, and how do you make them cost effective? And this digital thread of bringing all the engineering together is really going to help make that practical and accelerate the delivery of fusion power.
It's going to be challenging. I mean, how do you train people up? Because we're talking about a number of different challenges here that are very particular to your use case. But people who get conversant in programming languages or software engineering in general usually address different use cases. So, I mean, what kind of route do you take to help them ease into that area?
Sure, that's another really good question. We're about 2,000 scientists and engineers here at Culham, and probably globally there might be 10, 20,000 fusioneers, if you like. And we come from lots of different disciplines. We have traditional civil electrical engineers, we've got theoretical physicists, mathematicians, we have computer scientists, and a lot of other people that have come into through different career paths to the job they do today. And what we need to do, and what we are doing is finding the right way to get these interdisciplinary teams working effectively together. In my department, one of the groups that are really quite helpful with that is our group of research software engineers. Our engagement with the RSE community goes back about 10 years, when a member of our data science group went off to a conference. In fact, I think she got a fellowship from the Software Sustainability Institute. This is a great leader, Alice Brett, and she came back and explained the message to us that this was the way to try and bring good software engineering discipline to those other scientists and engineers who might not have had the formal training in their career development. And that's been very successful.
2,000 is a very large number, so I guess that is probably still expanding as nuclear fusion moves probably from, as you said, the exploratory stage into the more commercially viable one. So how far away do you think we are?
Okay.
If you can actually hazard a guess. I know
Oh,
it's
I
probably
can give
quite
you
tricky.
I can give you various figures. So the sort of machine trajectory, there are two paths. There's kind of the conservative path, which is without assuming any sudden step changes in technology, can we get a workable net power out fusion device? And the global collaboration building ITER in the south of France are targeting that machine working by the sort of late 2030s, early 2040s at high power. So that's a demonstration of the technology. There's then intended to be a prototype power station beyond that. And for the European Union, the roadmap for that is targeting 2050. Now,
Right.
Korea are more ambitious. They're targeting that second prototype plant in around 2037. I don't know what China's timescale is, but they are very, very much invested in this technology. You've then got the more ambitious accelerated programs, which are looking at super high field magnet technology, which is in its early stages, but promises a lot and allows more compact machines. This is typically what some of the private fusion companies are doing, both in the UK, the US, and elsewhere. There are billions of dollars flowing into those private
Mm.
investment schemes. I think it was about 3 years ago, our chief executive went down to Whitehall and explained why our technology was really critical to solving future climate problems and why the UK had a particular advantage and lead, and said, we propose that we should build, just using UK resources, a spherical tokamak for energy production, and that gives us the acronym STEP, and we would like to do that by 2040, and we seek your support. And you know what it's like when you go to ask for funding from government for a lot of money
Yes.
for quite an ambitious project. Luckily, our CEO is extremely persuasive, and they said, "Okay, how much do you need?" And we got the preliminary design funding about 3 years ago, and
Hmm.
we're on the journey of doing that design, and we're on a process of selecting a site to build this device, and we're expecting to really ramp up. So the future of Culham, we've got 6, 7 different major research areas, all of the complementary technologies for fusion. And it's the fueling and the heating and the materials and the control and the robotics. And we've got the backing of the UK government to try and do it. And I think that backing is only getting stronger. The other side, even in the States have been up and down on fusion a little bit. But just
All
yesterday,
right.
they had a major presentation at the White House
Mm.
with all the top leaders saying the States are now going for a 10-year sustained fusion program, really focusing effort and being serious about delivery. All our leaders are saying we are in the era of fusion delivery. 2040 or just ahead of that is the time scale that people are talking about. But given the exponential rise in private investment in the industry, it wouldn't surprise me if that timescale actually comes down. So
All right.
my,
I
my,
think that's
my guess would be
mm.
2035, 2036.
So not that far off, and certainly in within our lifetime, by the sound of it.
Absolutely.
Well, that's quite exciting, and I'm sure that there are plenty of opportunities for aspiring nuclear fusion engineers. So, how do people get into this? I mean, what's the typical career path into this?
I was interviewing apprentices yesterday and today. We've got a great
Mm.
apprenticeship program on site here. We hire people across various different engineering disciplines, including computing and electronics. We've got a very strong graduate program. And actually, feeding into the graduate program, we have people on placement. So maybe they've done 2 years of their undergrad. They'll come for a year at Culham, learn some of the skills, go back, finish their degree, and then usually we try and hire them. And quite a lot of people come to us through that route. We've sort of tripled our numbers in the last 3 years, so we've got a lot of new colleagues coming in from other industries. And actually, what I should have said about STEP is the goal for STEP is that that's not going to be something that the UK AEA, who I work for, build. That's going to be a really big collaboration with industry. So we're expecting probably 50% of that machine design will be done by large industrial partners. And what we're trying to get going here at Culham is a sort of fusion cluster center of excellence to help share our knowledge and research experience with that growing supply chain for the fusion economy. People can come in at any level. It can be your entire career starting from age 16, 17, and people are joining also at the higher levels of the organization.
The final question that I have is because you mentioned ITER in France, and obviously you're working for the UK, but there is a lot of international collaboration happening, isn't there, between the different centres? And
Absolutely.
Where does your organisation sit in all this? Is it still part of the European framework?
Yes, so actually over the last 10 years, part of my role is working with partners, often working with UK and industrial partners, to respond to calls for expertise from ITER, which are formed as formal contracts, and then to deliver science and engineering. We also have more collaborative programs working together. It's been a little bit difficult post-Brexit. All of the intent in the scientific collaboration space is that things should proceed once everything settles down in the same way it always did. There are one or two administrative wrinkles to iron out, but the goodwill on both sides is there to continue the collaboration. And we're also strongly collaborating with groups in the States and with other private partners in the UK and around the world. So yeah, I've got a great link with a team in Madrid, quite often down in Barcelona, where the technical teams for ITER do their procurement. We've got some great partners in Germany and lots of fantastic Italians and Portuguese. One of the great things, we've got, I think, 65 plus nationalities working here, and it is a very international, collaborative, friendly environment. That's another great reason to work in fusion.
Thank you very much, Adam. That was a very exciting interview, and I wish you all the best for your future, and of course to nuclear fusion, which is the holy grail of energy production that we've been waiting for a while.
Well,
so good luck.
It's coming, and it's been great to speak to you, Peter. So thanks very much.